Hello my friends and welcome to this new practical tutorial, and actually the last practical tutorial of this module on linear regression. So we've done everything, we've built the model, we've trained it, we've got the R-squared to evaluate our model performance, but an even more relevant metric to use to evaluate our model is the adjusted R-squared, and that's exactly what we're going to do here in this last tutorial to really get a good sense of how good our model is performing. Alright, so let's create a new code cell, and I hope you tried to compute the adjusted R-squared by yourself first. You know the formula, and so the first step that you had to do was of course to get the hyperparameters that are needed in the formula, right? Indeed, in the formula we have k, the number of features, or the number of independent variables, and n, the total number of observations in the test set, right? It has to be in a test set and not in a training set or the data set. And the way to get those two values very quickly and efficiently is thanks to a certain attribute of arrays in Python, which is the shape attribute, and which will give you exactly the dimensions of your xtest array. And since the dimensions of your xtest array are exactly what we want, meaning the first dimension is the number of rows, and that's exactly the number of data points in xtest, and the second dimension is the number of columns, and that's exactly the number of independent variables, or features. And so we're going to get those two values thanks to the shape attribute. So let's do this. We're going to call our array first, so xtest, and then from our array we're going to call this shape attribute, and since it returns the dimensions of your array, well, in order to get the number of columns we're going to enter in square brackets 1, right? Because that's basically the second dimension. You know that indexes in Python start at 0, so 0 would be the number of rows and 1 is the number of columns, right? The second dimension. And that, the number of columns, is exactly the number of independent variables. And for the number of observations, data points, well, we are going to take the same thing, xtest.shape, but instead of 1 here, we have to enter the first dimension, which has the index 0. Alright, so this gives us the total number of features in xtest, meaning the total number of independent variables, and this gives us the total number of observations, total number of data points in xtest, and that's exactly what we need to compute the adjusted R-squared, right? Because indeed, you know the formula to compute the adjusted R-squared, which we're gonna call here in a variable adj_r2, well, is, remember, 1 minus the R-squared times the total number of observations, meaning n in the test set minus 1, divided by the total number of observations in the test set n minus the total number of independent variables k minus 1. And there you go, my friends, we have our adjusted R-squared. And so we're going to run the cell to first get it, and then we're going to display its value by just calling our adj_r2 variable to get the value, and the value is 0.932, which is very good and reinforces, the fact that we have a performance model capable of making good predictions. Alright, so there we go. We're done for this first practical section on linear regression. Congratulations for implementing your first model. We're going to implement many more in this learning path, and the next one will be logistic regression in the next practical session. I look forward to building this new model with you, and until then, enjoy machine learning.